In the previous video, we talked about how we can measure what an average result of the data would mean and how we could calculate that in various ways. In this video, we're going to talk about measuring something called dispersion. So again, that's kind of a weird word, so let me kind of define it here. This is how spread out the data is. Like for example, let's say you asked everyone how many siblings they have, and we start taking down data here, and these are the numbers we're getting. All those numbers are really close to each other. So we would say they're not very spread out. Whereas if we ask everyone, say, age in the classroom, maybe we have something like this. Just making it random numbers now. Again, you see in this case, the numbers are a lot more spread out, a lot further apart from each other. So that's the type of thing we're trying to measure now. So we're calling it dispersion. And there's going to be two main ways we're going to do that. One, which is really easy to calculate, but unfortunately not all that useful. And another one, which is much more difficult to calculate, but is actually going to be the one we're going to use from here on out. So the first one's called range. And to find the range, it's literally just the biggest data value minus the smallest data value. Okay, that's all you have to do for the range. So this gives us a very quick number that says, hey, this is how much data is spread out. There are some problems with this. For example, what if most of your data are close together and then someone has maybe 8 siblings? That would drastically change your range, whereas the data is still pretty close together. It's just kind of one person off on their own. So range, it's not amazing, but it's very quick and easy to use. And sometimes we will want to use that just to talk about what's going on. Now, the one that's way more useful for us in future sections is called the standard deviation. Now, in order to build up to that, we need to do several things here. First off, and we're going to start with the population one, and then we'll do the sample version in a moment. So let's say I wanted to calculate the mean, and you guys may or may not remember that to find the mean, you add up all the values of x and divide by how many people there are. Now, what if I wanted to say, okay, that's my average value. How far away is any one data point from it? So if I take one of the data points, x, and I subtract mu, this is how far away the data is from the mean. And so if we say, okay, that's how far this one data point is away from the mean, why don't I look at how far away all the data points are from the mean, and why don't we just add them all up? And then we'll see how far we are total away from the mean. Well, it turns out if you add up all these distances from how far you are from the mean, it's actually guaranteed, no matter what data you have, it's going to work out to be 0. Essentially, there's going to be an equal number of data points that are kind of, it's not an equal number, but an equal amount above the mean as an equal amount below the mean. You can't, for example, have an average of 10 and all your data values are above 10. That wouldn't make any sense. So your average is kind of splitting things up, and as a result, if you just add up all these differences here, it's never actually going to give you anything meaningful. It's just going to give you 0. So what they decided to do is say, why don't we, instead of doing that, let's square all of those numbers so that everything is going to be positive here. So we're never going to have any of that cancellation. And then let's kind of take an average of those results. And this, we're going to use the Greek letter here. So this is lowercase sigma. And we're squaring it here. This is the population variance. As I warned you, this formula is kind of messy. It takes a lot of work to actually implement. So what you'd have to do if you wanted to actually do this by hand, you have to take your data values. First off, calculate your mean. Once you've calculated your mean, for every single one of those data values, you need to subtract that value from the mean, or I should say, that value minus the mean. Then you're going to square it. Then you're going to add up all those different numbers you just calculated, and then you're going to divide by how many there are. And after all that work, you get the population variance. Now, if I gave you like, I don't know, 4 or 5 data points, you could do this calculation in maybe 5 minutes. It's not too bad for a small number of data points. It's not very pleasant, but you could do it. However, if you were to give, say, 1,000 data points, then you're really never going to get finished. I mean, it takes way, way too long to do it. But as I said in the last video, I'm not going to make you do all these things by hand. I will show you how to use your calculator to do all the hard work in calculating this variance. Now, variance is useful, but quite often we don't want the variance. We want something called the standard deviation. And that's just without the square there. So you're still squaring inside. You're still adding them up. You're just square rooting your final answer. This is the population standard deviation. And this is the thing we are going to use over and over and over again in this class. The thing you might have seen in your life that's basically like standard deviation. Let's say you want to drive somewhere and you're like, oh, it'll take me 30 minutes plus or minus 5. Guess what? That plus or minus 5, that 5 there, that's essentially your standard deviation. It's saying, it might be plus or minus that amount, might be off by a little bit there. That's the type of thing we're trying to measure here, and this is the formula by how you would do that. Now, this is again true for the population data. You can do the same thing for sample data, but we're going to use different letters here. We're going to use S squared and S for the sample variance and sample standard deviation. Remember, for population ones, which are parameters, we use Greek letters. For sample ones, which are going to be statistics, we use regular letters. So sample, standard, deviation. Now, the formula here is a little bit different. So you're still subtracting the value minus the mean, which is x bar. But this time you divide by n minus 1 instead of n. Now, I don't want to get into that right now, but we will talk about it in a future video why it's n minus 1 and not n. But just know that the formula is slightly different for the sample compared to the population. Essentially, what ends up happening, here's a very quick breakdown of why we divide by n minus 1. If you had picked n there instead of n minus 1, you'd end up dividing by a bigger number, right? Dividing by n, and the answer is smaller. And it would turn out that on average, the answer you got for this would be underestimating the true variance and standard deviation. And so in order to try to account for that underestimation, they divide by a little bit smaller number, n minus 1, and it turns out that fixes it. Now, there's a lot of math involved in why that makes it work out well. I'm not doing that just now. We won't even do all the details just yet, but we will talk a little bit more about it in the future. Just know that there's different formulas here. Once again, don't get caught up in the formulas because we will see, put in your calculator and it gets the answer. And in fact, when we do variance and standard deviation in our calculator, and you put in your data and you hit your button that says calculate, they're going to give you both the population version and the sample version all in one go. You don't have to go and do two separate things here. It goes in both there. So the real difficulty for you is going to be knowing which one to pick. Do you pick the one they tell you where it says sigma, or do you pick the one that tells you that says S? So you need to understand whether it's a sample or population problem. Okay, so this is how we measure range. This is how we measure variance and standard deviation, both population and sample. Now we're going to use this. Now the empirical rule, first off, warning here, this only works for bell-shaped distributions. That's all it works for, so you don't try to use this on a uniform. Don't try to use this on the skewed left or skewed right. It has to be a bell-shaped distribution. And it tells us the following here. the percentage of data within plus or minus 1 standard deviation of the mean is 68%. So what that means is if you find the average of something and you find the standard deviation of something, and you say, okay, how much am I going to be in there plus or minus? So let's say that trip there takes you 30 minutes plus or minus 5. Well, what happens if you do actually do plus and minus 5? So 30 plus 5 is 35. 30 minus 5 is 25. So if you look at how many trips are you going to arrive, and it takes between 25 and 35 minutes, it's going to happen about 68% of the time. Now, this is not a perfect exact number. This is an approximation, but it's saying about 68% of the time you'd arrive between 25 and 35 minutes. And then the other times, maybe there's extra traffic to make it take longer, or maybe the under times is you got all green lights everywhere, whatever it may be. But 68% of the time, roughly, you're in that range. Let's make up another number here. Let's say the average adult male height is 5'10", and let's say that the standard deviation is 2 inches. Again, these are probably not accurate at all. But if I would say, okay, what happens if you add and subtract 1 standard deviation? So 5'10" plus 2 would be 5'12", which is really 6 foot. And if I do, mu minus sigma, 5'10" minus 2 is 5'8". So then we'd be saying that about 68% of adult men are between 5'8" and 6 foot. Now again, those aren't the exact correct numbers for what the mean and standard deviation are. You can look them up probably. But just to give a rough idea here, this is what we're saying within 1 standard deviation. And furthermore, if you want to say within 2 standard deviations, it's going to be approximately 95%. And if you want to be within 3 standard deviations, it's approximately 99.7. So sometimes the empirical rule is also called the 68, 95, 99.7 rule. Keep in mind, once again, this only works for bell-shaped distributions, but it gives you a quick and dirty way to say what percentage are going to be in this range. And we are, in a future chapter, going to learn how to do more accurate calculations, or what if, say, it's not 2 standard deviations, what if it's 2.5 standard deviations? This rule doesn't tell us that, but we're going to learn how to calculate that later. But for right now, this is the empirical rule, and we just use it for simple, rough estimates at this point in time. And then the last thing here, which is something that we're really going to hardly use in this class. It's a cool idea from a mathematical point of view, but it's just not super practical for us. And what it says, this, by the way, works for any distribution. This no longer has to be a bell-shaped distribution. And it says the proportion of data points within some k standard deviations is at least 1 minus 1 over k squared. So for example, let's say you have k equals 2. That means you are plus or minus 2 standard deviation. What this tells us is you're guaranteed at least 3/4 or 75% of the data are going to be in that range. You might say, why am I doing this? I already know there's going to be 95% from the empirical rule up here. Why do I care about this 75%? That doesn't really help us, but in fact it does, because And again, the empirical rule only works for bell-shaped. Chebyshev's inequality works for any distribution. So no matter how weirdly shaped your data is, you know that within 2 standard deviations, you're going to have at least 75% in that range. And if you wanted to say, well, what happens if I'm within 3 standard deviations? Just using the same formula here. 1 minus 1 over 3 squared, that's going to be an 8/9, which is about 89%. So again, it's guaranteeing that within 3 standard deviations, at least 89% of your data is going to be in there. Now, likely it's going to be a lot more than 89%. Anything that is relatively well behaved, it's going to be significantly closer to this 99.7 number. But even if you had the craziest data set ever, it's still going to be at least 89% within 3 standard deviations. So this is why, we say we're trying to figure out outliers and how, what means to be an unusual data value. Sometimes we'll say if you're more than 2 standard deviations and more than 3 standard deviations, then you're pretty far out there. You're pretty unusual. But there isn't necessarily a hard and fast rule for that. Anyways, key things in this video is how do you calculate range? How do you calculate variance standard deviation? What are they? What are the symbols for them? What is the empirical rule? And what is Chebyshev's inequality?